Good day everyone. My name is Muhammad Amshar bin Jamaluddin. Today we will delve into an intriguing problem that combines geometry and calculus, focusing on the application of differentiation. Our topic is closely tied to the concept of optimization, which plays a pivotal role in various fields such as engineering, economics, and physics. Optimization involves finding the maximum or minimum values of a function, and in this case, we are exploring the maximum volume of a composite cylinder. We begin by examining a figure that shows a small closed cylinder placed on top of a larger cylinder. The problem challenges us to work with the surface area and volume of these cylinders to achieve an optimal solution. Azami will start addressing part A of the problem, which he will express the height h of the small cylinder in terms of its radius r, given the total surface area. Following that, Kais will handle part B, demonstrating the volume of both cylinders, and finally, Akmal Fikri will tackle part C, determining the radius r that maximizes the volume and subsequently finding this maximum volume.
So we move to question A. First, we must identify the surface areas of both cylinders. For A1, we use formula 2 pi r squared plus 2 pi r h. For A2, we use 4 pi r squared plus 8 pi r h. And then we combine the surface areas of both cylinders and set them equal to 350 cm squared. And we get A1 plus A2 equal to 350 pi. After that, we substitute the expression for A1 and A2. We will get 2 pi r squared plus 2 pi r h plus 4 pi r squared plus 8 pi r h equal to 350 pi. And then we simplify the equation by combining like terms. From 6 pi r squared plus 10 pi r h equal 350 pi, we will divide both sides by pi, and we get 6r squared plus 10rh equal to 350. And then we will solve for h in terms of r. We will subtract 6r squared from both sides and divide both sides by 10r. After that, we will simplify the expression and we will get 35 minus r squared divided by r.
Let's proceed to the problem solution question B. First, we have to remember the formula. V equal to pi r square h, V1 equal to r, V2 equal to 2r, h. We get it from question A, which is 35 minus r square over r. To find the V, we have to add the V1 and V2. V1 r, V2 2r. So include it to the formula. V equal to pi r square in bracket 35 minus r over 35 minus r square over r plus pi in bracket 2r square and in bracket 2 times 35 minus r square over r. So let's simplify it. We get it V in bracket pi r times 35 minus r square plus in bracket 4 pi r square times 70 minus 2r square over r. So simplify it again. V equal to 35 pi r minus pi r cube plus 4 pi r times 70 minus 2r square, and the answer we get it 35 pi r minus pi r cube plus 280 pi r minus 8 pi r cube, and lastly we get the answer V equal to 350 pi r minus 36 over 5 pi r cube. So it is shown.
For the next question, we will go to question C. The question is determine R in centimeter so that the volume is a maximum. Hence, find the maximum volume of both cylinders. So in this question, it has two questions. That is determine R in centimeter and also find the maximum volume for both cylinders. So first of all, we need to find the R first. If we need to find the R, we need to differentiate the V first. That is V equals to 315 pi R minus 36 over 5 pi R to the power of 3. After we have differentiated, that is 315 pi minus 108 over 5 pi R to the power of 2. We will need to let the dV over the R is equals to 0. After we will have done it for the left side, we will do it equals to 0. We need to change the 108 over 5 by R to the power of 2 to the left hand side, so that the R will be to the left side. And after that, we will need to place the 108 over 5 pi to the right side, and it becomes divided by 315 pi. And after that, we will get 175 over 12. And then for the R square, R to the power of 2, we will need to change it to the right side, and it will become 100 square root 175 over 12. And then we can simplify it by 25 times 7 square root, and also square root 4 times 3. After that, we can simplify it until it becomes 5 square root 2 over 6. That is for the first question. That is for our question. Next, we will go to find the maximum volume of both cylinders. So all we're gonna do is just put the R in our first equation, that is V equals to 315 pi R minus 36 over 5 pi R to the power of 3. Put the value R into the equation. So after we have put R in the equation, the value that we get is 101,202.93 pi minus 400.93 pi, 98 pi. And then after we have subtract both, we get 801.93 pi. And then we will change the pi to its value, that is 3.134. And then we will times 801.95 with pi, and then the last answer we will get V equals to 2,519.40 centimeters square. So that is the last answer for the question C.
In conclusion, we have explored a fascinating optimization problem involving composite cylinders. Through the collaborative efforts of Azami, Kais and Akmal Fikri, we have first expressed the height h of the small cylinder in terms of its radius r, given the surface area constraint. Secondly, demonstrated the volume of both cylinders. And finally, determined the radius r that maximizes the volume and calculated this maximum volume. This exercise highlights the practical application of calculus in solving real-world problems. By understanding how to optimize function, we can make more informed decisions in various fields. Thank you for your attention, and we look forward to any question you might have. Thank you.